with their names on the website. I'm not sure about that, but I hope they are. So with this, then until 5 o'clock, you can vote for the best poster. And I guess it's now for the next session. So I will give word to our, first to our chairman of the Justyna Grabska.
Hello, everybody.
Hello.
I think it's start our next session. And this is my huge honor and pleasure to be here. And thank you everybody for joining this session. Topic of the session is forces shaping the water beyond sensing to biomodulations. And I think it's a really interesting and important topic. And let me introduce our first speaker, Dr. Michal Cifra. I hope I'm saying this correctly.
Yeah.
Michal Cifra, since 2013, is a head of Bioelectrodynamics research team, Institute of Photonics and Electronics of the Czech Academy of Sciences. He did in 2006 his master's degree in the University of Žilina in Slovakia, and in 2009 his PhD in Radioelectronics in Czech Technical University in Prague. Apart from 1 year biophotonics research experience from Germany, he also gained experience with high-frequency bioelectronic interface. He spent 8 months in University of Chicago. The mission of Bioelectrodynamics research team is to advance probing and influencing biosystem using an electromagnetic field at the biomolecular level. The vision is to design novel electromagnetic methods for beginning and more efficient bio-nanotechnology and medicine to bring us closer to a world where electromagnetic technology can painlessly prevent, detect, and cure disease. Topics of my first speaker is microwaves and nanosecond electric pulses for analysis and influencing of microtubule system. Please.
Thank you very much for a nice introduction, which made me easier to me to start. So thank you again. I hope you can see my screen. You can hear me and see my laser pointer. Okay.
Yes, we can.
So let me start with some vision, maybe it's a little bit science fiction. I hope you might be familiar with the one of the science fiction series of Star Trek. There was a device where which could be used to non-contactly diagnose and treat diseases, and was called tricorder. And we believe that this device must be underlying technology where we can influence the organisms using electromagnetic waves and also detect electromagnetic waves which can come from the organism. Basically, this enables the wireless and non-contact detection. So this is where our team comes in. We have a variety of the backgrounds in our research team, and it covers microwave engineering, biophysics, and physical chemistry. So as was mentioned, our mission is to probe and influence biomolecular systems, including organisms, using an electromagnetic field. This is what we plan to do through the lifetime of our research team. The vision where this should lead us in the future is to bring knowledge to enable novel electromagnetic methods for gentle and more efficient bio-nanotechnology and medicine. And the current tools which we use are advanced electromagnetic concepts, nanotechnology-enabled tools, and computational methods and simulations. So in our research, we explore both active and passive electromagnetic properties of organisms. That means how organisms generate electromagnetic field and how they are influenced by electromagnetic field. Based on these theory and predictions and modeling, we develop a new technology which enables us to probe these theories and verify these theories. And then we carry out experiments using the technology we develop to verify our predictions and theories. Mostly we are working on the cellular level and on a molecular scale in the current projects. So we perceive organisms to be very complex machines. However, we believe that understanding the parts is only one aspect of understanding the whole, because we also need to understand the interaction between the parts to understand the whole, which is absolutely necessary. So we try to combine both mechanistic and integrative science philosophy. In particular, in our research, we are trying to understand how biomolecular components and their interactions respond to electromagnetic field. So in our case, our favorite system is our tubulin and microtubules, which are part of every living cell, and they're particularly concentrated in a brain tissue. So why microtubules? Well, microtubules are essential structures for cell division, intracellular transport, and intracellular signaling. They are part of the cellular cytoskeleton, and they are interesting from electromagnetic perspective because the tubulin, the building component of the microtubules, have very high electric charge and dipole moment. Beyond this intriguing electric properties microtubules have, microtubules are interesting because of the innate dynamicity or dynamics. The microtubules, as you can see in this animation, they typically in the cell, unless they are stabilized, they permanently grow and shrink. So they undergo so-called dynamic instability. So they are essentially non-equilibrial structures, and this property of non-equilibrial self-assembly and disassembly can be also reproduced in vitro, meaning out of the cell. So they're a nice system of actually life, studying the life out of the cell. So in the first part of my talk, I want to focus on a technology of microwave devices, which we recently developed. We've developed resonant devices which can probe the electromagnetic properties of biological samples on small volumes, either in particular frequencies or in a broad band. In particular, I'm going to speak about our recent work where we developed microstructured chip for nanoliter volume analysis of microtubule self-assembly state. So what property of microtubules can we potentially sense using microwaves on the chip? So as I mentioned earlier, microtubules are, well, their state, it can be, if you view it black and white, you can see that microtubules are either self-assembled or polymerized, so they are tubes, or on the other hand, if they are completely disassembled, they are only basically in the sample you have only 3 tubulin heterodimers. So these are the two, let's say, two different part of the two different, let's say, poles of the situation. So either disassembled or assembled structures. So this is a very important property because it underlies the cell division and also other important properties in the biological life. So we said, well, let's try to analyze this property, the self-assembled state. So why this could be possible at all? And now this is where actually the solvent or particularly water comes in, because what is known is that when basically any polymer polymerizes, this is case also for microtubules, it affects effective viscosity of the solvent because the mobility of the surrounding molecules, in the case of microtubules, it will be water around the molecules, is affected. So if you assume this that the viscosity would be changed, that would change important property in microwave dielectric spectra, and that's the rotational diffusion time of all the biomolecules, including the solvent biomolecules, that means the water, and that would affect the microwave dielectric spectra. So this frequency is centered at 20 gigahertz interdispersion. However, we believe that in this case, because there are many more things happening in the sample and the microtubule polymerizes, we also need to understand the permittivity, microwave permittivity spectrum on a broader range. So the required frequency of operation of our chip was set to be very broadband, from 1 to 50 gigahertz, very broadband in terms of microwaves, because we believe that the self-assembly will affect the broader range of the permittivity spectra. The strategy in this work was to have, well, 2 samples, completely polymerized and unpolymerized tubulin. That means either tubulin unpolymerized or to polymerize into microtubules, and then compare into microfluidic system, measure the microwave parameters of these samples, and then from the transmission and or reflection to analyze if there is any difference in these two samples, and then try to analyze and then extract the effective permittivity of these samples. So I will briefly fly over our design so you can see all the details here. It's not important now, this engineering part. What I would like to mention is that we have a chip on it is roughly on a micrometer scale, which is connected to microfluidics on the substrate. This is how it looks fabricated. We have do all microfabrication in-house and also the design. This is one of the measurement chips look like this. These are the calibration kits. So it's rather small, but well, that's the point. We want to use only very small volumes because microtubules which are extracted are rather expensive samples. This is how the experimental setup looked like. Just in brief idea, this is the probe station, which enables to measure the microwave properties very accurately, even from small chips. This is the microscopic image of the microfluidic channel, which goes vertically, and the microwaves go along the chip horizontally and along this way. So this is just the zoom of the sensing area, and you can see some details of the microfluidics here. Now, our results are following. When we focus on the tubulin and microtubule samples, and now I will speak briefly about the other samples as a control later. We can see that there is, although on an absolute scale, there seems to be only a small difference in S parameters, means transmission of the microwaves through the sample. When we subtract the background, which we can, let's say, our reference here is the tubulin sample from the microtubules, we can see there are differences between tubulin and polymerized tubulin into microtubules. So you can see there are larger differences in the particular frequencies and at the low gigahertz and then on the higher gigahertz range of the spectrum. Now, when we go to the extracted effective permittivity, which tells us something more about the underlying physics, we can see that when you now focus on the differences of the spectra, because there we can see by naked eye differences between the individual samples, we can see that when we now focus on the differences between microtubules and the tubulin samples, this is the full line. If you follow me, you can see that there is difference both in the real part of the permittivity and also imaginary out of the permittivity. So if you can see at which frequencies there are the largest differences. So in short, we can distinguish microtubules and tubulin and believe, this is discussed in our paper, that the underlying physics is in the change of the viscosity, effective viscosity in these high frequencies because of the microtubules are polymerized and they affect the mobility of the surrounding water, not only surrounding, but also ranging further for microtubules. So in short, the take-home message for this part is that microtubules, we predicted the microtubule state can affect complex permittivity in the microwave range. We designed and fabricated a chip which can sense the microtubule self-assembly state, and then we extracted the real values, the absolute values of the permittivity, and also compare them between the samples, and that showed which are the frequency band where microtubules and tubulin show the largest differences in their microwave spectra. And we believe this is due to mostly due to the changes of the solvent caused by the microtubule polymerization. So this is basically water serves here as a biomarker. Now, to the second part, how to use electromagnetic field to influence biomolecular systems. So in our recent projects, we focused on nanosecond electric pulses and how they can be used to modulate the cellular skeleton. And we want to have a mechanistic understanding starting from the components, as I mentioned, to the larger systems. So we started from molecular dynamic simulations. But to give you an idea, why we're focusing on the nanosecond pulse electric fields to affect as a one of the potential forms of electromagnetic field? Well, the reason is that nanosecond pulses are they contain large, the broad spectrum of the energy in these pulses contained in the broad spectrum, reaching up to the radio frequency. So these pulses potentially can also propagate through the air and also can propagate through the tissue. So in future, for potential therapies, these pulses can reach a deeper part of the organism compared to, for example, the light or the infrared or terahertz bands. So this is one reason why to use nanosecond, because of the broad spectrum. And the second reason is that within short duration of nanosecond pulses, we can achieve very high field strengths, reaching even tens or maybe hundreds of megavolts per meter, without heating. So this is very important, because if you typically people use high powers, they cause heating of the system, which we do not want. We want to study non-thermal electromagnetic biological effects. But this, in this nanosecond pulses, we can achieve high field strengths, which overcome thermal forces and also overcome also molecular bonds while not heating the system. The third reason why to use nanosecond pulses is that in simulations, these pulses are short enough to be computationally tractable, meaning that we can execute full atom molecular simulations. In all simulations, I'm not showing the water motion, just for the clarity. I'm only showing the structure of the proteins, but we always, of course, include in our molecular simulations, full atom molecular simulations, we include the atoms and the necessary ions in the system. So now starting with the theoretical predictions, meaning we are working now in silico, in computer. So what we found is that in our model system, tubulin, which I mentioned earlier, is that when we apply electric field, let's say here 20 megavolts per meter, within a few nanoseconds, the tubulin protein can orient within along electric field. And if we apply even stronger electric field, again within a few nanoseconds, it's not only dipole moment, here the orange arrow, which aligns with electric field, but also for the higher field strength, the protein structure seems to be changed. So the message is that we probably are able to influence protein structure by the electric field. Further analysis which we performed, I'm not showing the details, just the message, is that the electric field can affect the shape of the protein, either reversibly or irreversibly, depending on the electric field duration or the field strength. It also affects dipole moment. For the sufficiently strong electric field, it can also affect the secondary structure of proteins. And importantly, we notice also that the electric field can transiently affect functional sides of the protein. In our case, tubulin, it was the drug binding pockets and nucleotide binding pockets, as well as tubulin-tubulin interaction sites. So this gives us a hope, these simulations, that we could see something in experiment. So is it really so that we can confirm at least some of these in experiment? So that's why we carried out experiments on isolated biomolecules. That means experiments in vitro. And this was the following protocol. We took in the sample of to the tubulin. We applied electric pulses with these parameters. We varied from a few hundred to even 800 pulses in our experiments. And after that, after this treatment, we characterized by autofluorescence, dynamic light scattering, as the potential, the changes of the tubulin. And we found in all of these, we found some. This was first part of the experiment. Then we took the electric pulse treated tubulin, and we induced the polymerization of, we set settings, an experiment which normally induce tubulin to polymerize into microtubules, to self-assemble to microtubules. After that, we characterized again the outcoming sample. So typically it's microtubules with turbidimetry, atomic force microscopy, and autofluorescence again. What we found in general, and this is the main message, is that electric field, also in experiment, electric pulses, these short nanosecond electric pulses can affect tubulin heterodimer. And importantly, this effect can be reversible within a certain range of electric field, electric pulse parameters, which is very important because if we exceeded certain range of parameters to strong fields, let's say, or too many pulses, the changes were irreversible. So it's important to have this tunability, and which we demonstrated in our paper. So in this curve, you could see that it's not only tubulin structure which was affected, but we also affected. This is basically the absorbance gives us amount of microtubules. So for untreated tubulin, we could see there is certain self-assembly polymerization curve. But for the treated tubulin, we found that the kinetics of polymerization to microtubules, to self-assembly to microtubules, is different. And we found then using atomic force microscopy that while for untreated tubulin, tubulin forms rather normal microtubules, depending on the strength of the treatment, the treated electric pulse treated tubulin forms different structures, or either some flat, well, closed tubes, or the tubulin walls which are open up. So the main message here is that we could demonstrate that the tubulin affected by electric pulses can form also different structures than microtubules. So this has important implications in both in bio-nanotechnology in self-assembly, but also for the applications in potentially in a cancer treatment, because we could affect, maybe by using nanosecond electric pulses, we could affect microtubules, so we could maybe prevent the cells from unwanted division in a oncological therapeutical protocols. But this is still a question for the future research. Now, the question is, could we observe these microtubule modulation effects also in cells? So in order to address these questions, we performed experiments in vivo. But for these, we needed a particular new technology. And for that, we developed a new microscope embedded chip assembly. So the point was there to find the proper way from engineering perspective to connect a nanosecond high intense electric pulses generator to the chip, which was meant to be sitting on an objective of the microscope. Well, it was more fancier microscope. We use super resolution microscope to see the details in the cell structure. So this is this is actually original work which we performed. So I'm showing that we engineered the whole chip assembly. This is all done in a house in our workshop, and this is done in our microfabrication facility in our institute. So basically, what you can see here is the chip. Basically, the gold pattern on the glass, where there is a coupler waveguide which guides the pulse along the chip. Then the feeding part, which enables its connection to the cables from the generator, and the microscope holder, which is particularly dedicated, so it's easy to use for biologists and even for let's say non-engineers. So the principle of the experiment was the following. So we have the chip assembly. Then we, in microscope, we focus on a tapered gap between the electrodes where there are individual cells. And then we probe the fluorescence image using both standard fluorescent and also super resolution microscopy on the level of the single cells. And we are focusing on a cytoskeleton, particularly microtubules. So these are the results. I'm just going, I don't going to show you the details, but the main message. You can see on the left the control image, simple video from few frames of fluorescently labeled microtubule end binding proteins, EB3, which form so-called comets. On the left, you can see how these normal comets look like in rat basophilic leukemia cells. And on the right, you can see how this cytoskeleton structure looks after the treatment by electric pulses. So we can see that the cells are affected by this these nanosecond pulses. However, we found in other experiments that the cells can also recover. So again, we found a range that which is where the cell we can remodel, actually modulate the cytoskeleton structure without killing the cell. So it is important. Again, we have some tunability. We could also kill the cells with exceeding number of the pulses, but also we can only, let's say, gently remodel the cytoskeleton without actually killing the cell, which is, I think, important for our future therapies to find modalities which are tunable. So in summary, for the second part, we found in the simulations that tubulin can be affected, a single protein can be affected in terms of its structure and shape and dipole moment. Furthermore, they demonstrated in experiment that in these changes after short electric pulses take place on a tubulin, on this protein. And in experiment, we found that these electric pulses can affect, well, something similar to predicted in a simulation, and that's conformation of the tubulin and also self-assembly of the tubulin. And then we demonstrated that microtubule structures are also affected by nanosecond electric pulses with the similar parameters, also in the cells. And for that, we developed new chip technology, and we've demonstrated that microtubule network can be remodeled. Here, however, I have to mention that exact mechanisms in the cells are much more complex. So we believe that in the cells, we are, of course, not affecting only microtubules, but we are also affecting strongly the membrane. And the effect which we see is a compound effect of not only effect on the microtubules directly, but also of other downstream effects from the microtubules, which is one of the future work which has to be carried out. However, for our research, what we believe is important next steps are to explore the effects of nanosecond pulsed electric field on other cytoskeletal components. That's what we are carrying out right now in, let's say, on a protein and nanomotors, which work on the microtubules. In our current big projects, we also explore the effects of intense sub-terahertz pulses, basically intense millimeter wave, let's say, band of electromagnetic pulses on cytoskeletal structures. And also we are focusing on engineering of enhanced electromagnetic field biomatter interaction. So these are our collaborators who enabled us to help us with the biological part of the experiments. And I would like to highlight that this week is also special because it's a biophysics week. And last but not least, if you are interested in our research, we started recently organizing regular twice per month bioelectrodynamics webinars, and if you can find more info on our social media channels, and I will be glad to take any questions. So thank you very much.
Thank you very much. It was really interesting. I think we have now time for questions. I see that there is one question in the chat. Should I read it? Or maybe it's...
I try to switch to chat if possible. Second. If I ask you to read it before I get there, it will be fast.
Michal, Pierre speaking. Can you hear me?
Yes, I can, Pierre. Hi.
Nice to see you again. I just posted this question on the chat forum. The issue is, the main point is, the Jardine effect actually works with low frequency in the ELF band.
Yes.
You're using high frequency nanosecond pulses. Is there any repetition frequency applied in the ELF band? It means you have a nanosecond pulse, but you applied in the low ELF region in a repetitive pattern?
Mm-hmm. So I'm not showing it here. Yeah, I'm sorry. I only see in the merge report. So yeah, we use mostly a few hertz to a few tens of the hertz.
That's the point. That's the point. Thank you. That's the point. Yeah. Well, that brings me to the second. If I can ask a second question, can I?
Yes, of course.
Okay. Thank you, Justina. The underlying dynamics, as you outlined it, obviously pinpoints the viscosity properties of water. If we look at quantum electrodynamics, then we find viscosity changes within the flipping of coherent to decoherent clusters of water. So according to that, what you said, I assume that this is indeed a quantum electrodynamic effect. So can you maybe elaborate a little bit more on this particular detail?
Well, we didn't consider quantum aspects here because the, well, you know, typical explanation of, which is for me satisfactory, of changes when the polymer polymerizes is basically because it grows larger structures which are less mobile. Then it also makes surrounding solvent molecules, in this case water, less mobile. So this is basically as simple as that. Of course, there could be more elaborate effects. For me, in general, it's very peculiar that even a few % of the solute, in our case, microtubules, can affect 99.999% of all surrounding solvent, which is interesting. So it, of course, there are some interesting long-range effects, but I mean, probably will be too far stretched to to directly go to the quantum explanation, because there is plethora of effects which can be happening there. But it's definitely very interesting. Just the mere effect.
I see. Okay, I see. Well, we can discuss this on a personal level. May I ask a third question, or I'm out of time?
Yes, we still have them.
Okay.
We can have a discussion, by the way.
Yes, we missed you. We missed you during post session.
Yeah, I had troubles accessing the it wasn't okay. Anyway.
Yeah.
No, I'm sorry about that. The final question would be the power density that you apply in the nanosecond pulse. I mean, as Livio Giuliani pointed out in his work, that you don't need to have huge intensities. It's sufficient to have very low intensities as long as you have the geomagnetic field present. So why then opting for high power exposure systems?
So for electric, I mean, this is magnetic field and magnetic field combination, what you are saying. For electric field, simply, if you don't apply field strong enough, we don't see effect. I mean, it's simple like that for us in our experiment. Of course, you could try to purely on other let's say settings, but I mean, physically it makes sense for us to use megavolts per meter and short pulses, because these, when you look on forces on the molecular scale, these forces of electric field are strong enough to affect the molecule. So it's a very straightforward approach. I mean, yeah, of course, you could try to play around with the background field, but this is very difficult and complicated to do, I mean, at all to control. And I think it more relates to combination of the magnetic fields and their, let's say, combination of the static and alternating ones and their angles, I mean, of the vectors. But for electric field, I think this might be a little bit different story.
Now you triggered off some other questions, but I'd rather stop. Otherwise, we dive into new method shielding and all these other things. Okay.
Yes,
okay.
I just want to welcome you both. I know that we can talk forever. It could be an endless discussion, but let me use the opportunity to congratulate Michal for the wonderful projects that you and the aggressiveness in a positive way that you have in approaching all this research, and it's so important.
Thank you very much.
It is really very nice to see every year how and the direction that you progress. Listening to you, I was thinking about there are papers already out there talking about having coherent and non-coherent frequencies, which means that there might be very dangerous frequencies for people. And of course, you're talking about using different frequencies to reshape microtubules, reshape other proteins, change functionalities, obviously. Well, we're talking, so you're focusing on proteins and microtubules. We're focusing on water, and I wonder at which point you will start working on both of them.
Well, we actually do. It's just, to be honest, we just work with something which is straightforward and direct, right? Of course, we looked on, let's say, how electric field affects the water around the microtubules. So it's interesting. But we haven't published those things. What I think our more, let's say, stronger role could be on actually seeing the water dynamics in a different frequency bands when water is close to proteins. But because the proteins and anything, basically any biomolecule, will affect strongly the dynamics of the water, and that's what we can be powerfully probed by the molecular dynamic simulations when coupled to experiment. So, for example, in our case, since there's important band of the water absorption dynamics in the 20 gigahertz frequency in microwave. So this, I think, there is a lot of work that can be done, and it's very interesting where we can see.
Terahertz, gigahertz, all these pulses, I mean, they do change water structure, obviously, and I'm very happy that you show it. We can see it, but how exactly they influence the molecule, and more importantly, how exactly they influence the water. I think you better go, because I saw your spectra, your terahertz spectra. It's not that informative of water, right? So if you go to infrared, near-infrared, so especially near-infrared, then you can non-invasively monitor and see the dynamics of the water, and then you see that might give us a clue what is good and what is not.
Yeah, definitely it's interesting to expand the spectral band to probe. And yeah, as you are saying, we are seeing different things in microwaves. It's rotational dynamics typically explained like that, and you can see more subtle things in infrared because you have some sharp spectral peaks which you can sensitively probe. So definitely it will be a great combination.
When you look at water, you look at the system, and you can say exactly if this particular perturbation with this particular frequency is good for the system or it is bad for the system. Looking at the single
this bad
tracking,
and good is something for me, is there qualities which are absolutely essential in our life?
Yeah.
But how to, assign numbers to good and bad? I mean, it's usually a biological outcome,
absolutely,
right?
Absolutely. But then it depends on the system and the status of the system and what you want to achieve. So you need a feedback, and you need definitely a feedback. When you control perturbation, you are focusing on the perturbation, right? So you want to influence the system, but then you want to know if your influence is right or wrong. So you need immediate feedback. And the immediate feedback comes from the system as a whole.
I see.
Not from a single pieces. So that's why I think that looking at the water, that wraps up all the system, and all the information is in the water. So if you can follow the water in the various details, then you get lots of information for that particular, for functionality in general. So
that's very interesting. Yeah, definitely it's inspiring. We would like to embed those things. We are focusing, I would like to make sure not to stop Pierre from starting. We are mostly focusing on biological outcomes. So we are trying to use these advanced microscopies to actually see how the behavior of the system changes by looking on it.
Yeah.
Of course, structurally and mechanistically, so to say, to see deeper, we need to go to spectroscopies, and it includes, of course, infrared spectroscopy. We can probe the things. Yeah, thank you very much for very interesting comments.
Thank you. So I know that we went the same like with you. When you start with Pierre, somebody has to stop us. So.
So in this case, it needs to be me.
Yes.
And thank you very much for a very nice discussion. I also see that in chat there was one more question, but I need to ask you to move the conversation to the chat.
I will respond in chat.
Yes.
Thank you very much.
And we're going now to the next speaker, Dr. Pierre Madl. And he originally trained in electrical engineering and later in electronics. Works in this field as a professional for over 10 years. Intrigued by this phenomenon of life, he enrolled as a part-time student at university in Vienna, Salzburg, and Brisbane, which in 2003 earned his master's degree in environmental science within a joint academic program between the universities.